Hi, we are Team 6 and this is a demo video of our programming language day. I am Deepika and I will be talking about the features of our language. Day has a simple syntax like C and it is block structured like Java. The execution begins at main block. It is strongly typed and the variables must be declared before they are used. Our language supports the data types int, bool and string. It supports mathematical operations like add, subtract, multiply and divide, and conditional operators less than, greater than, less than equal to, greater than equal to and not equal to. You can define functions with or without parameters and with or without return values in Day. We have also handled recursion. Further, we have the if-else decision construct, the while looping construct and the stack data structure. Lastly, we have taken care of the global and local scoping, and the scope resolution happens at runtime. The Day programs can be executed from the command line. Moving on to the tools and technologies, we have used Antler to define the grammar and parser, and the runtime is coded in Java. We have used the Eclipse IDE. Here are the list of keywords used in our high-level code and the corresponding intermediate code.
Hi, I'm Aditya. I'll start with how a code is translated into output in our language. Now the user writes the source code and the grammar tokenizes it using our lexical analyzer. Then the parser converts all the tokens and then groups them into intermediate code. Now this intermediate code is interpreted by the runtime and converted into the output. The next part is grammar. To understand grammar, let's have a look at a sample code. Now this sample code has all the basic commands to understand the grammar. Now let's build a parse tree for this sample code. As you can see in our sample code, the starting point is main program, which has two nodes, program and main block. The program node can have a variable declaration or assignment or a function declaration. On the other hand, the main block should have two keywords, start and end. And in between them, it will have statements which again include print, if else, while and function call statements. Our variable declaration node can have num, bool and string values. Function declaration should have a return type which can also be void, and if the return type is not void, it will have a return statement. The expression node handles all the operations like plus, minus, multiply, etc. And one more thing, our main block should be at the bottom and all the declarations have to be declared at the top of the code. Let's have a look at how the intermediate code is generated. After we write our high-level language, Antler uses the grammar file to create various classes like base visitors and tokenizers. The parser then creates the parse tree using these classes. Now to visit each and every node, we create a myVisitor file that overrides the visitor functions to what the developer wants to do. The myVisitor class traverses the tree and creates a set of instructions which are printed into a .dpp file. Now this .dpp file is our intermediate code which is later used by the runtime.
Hi, I'm Yoga. Let me brief you through our runtime. Our runtime is written in Java. Runtime takes intermediate code as input, executes it, and writes output to the console. Let's shift to runtime code. We have used hash maps to store global variables, another hash map to map function name with its corresponding block of instructions. We have a temporary stack to evaluate expressions and resolve function calls, another stack of block values to take care of global and local scoping. So this is our block values class, which holds reference to the parent block and local hash map of variables. Our runtime takes the intermediate code and reads it line by line. Let me show you a simple example. So this is our simple function call program. Variables in global scope are stored in global hash map. Hence, A and B values are stored in global hash map. Whenever function block is encountered, a block object is created and the reference is stored in the hash map. Since example and main functions are functions, they will have entries in the function hash map. Once the whole program is parsed, execution starts from main block. A local hash map of main variables is created and is pushed into the stack. When fcall example is encountered, instructions are fetched from the block and are executed. As a result, a local hash map of example variables is created and is pushed onto the stack. When print A is encountered, the local hash map is scanned. If the variable is not present, then the parent hash map is checked. Since here global hash map is the parent, A's value is retrieved from global symbol table and printed. Once the function is completed, the hash map gets popped off the stack. Control returns to main and remaining instructions are executed.
Let us now see a demo of how to run the day programs. So this is the high-level program for a Fibonacci series, and the counter is set to 5 here, and this is our while loop to control the execution. To run our program, we'll place the program files as well as the jar in this particular location, navigate there, and then using this command, we would execute it. So as you can see, now the first 5 values of the Fibonacci series are printed. So our program generates the intermediate code and it is stored in the same location. So let us have a look at the intermediate code. So the declare keyword is used to initialize the variable, and using store we can assign values to it. So our main block is governed by fdec main and an fend, and a while loop is governed using the loop followed by a label and has a corresponding endl followed by a label with whatever statements to execute being inside them. We use the jump keyword, and that is used to jump back to the same loop label and execute the statements over and over again till this condition becomes false. So since in our runtime we have stored all the loop execution statements inside a block, each time we call jump L0, whichever is the label, that corresponding block is fetched and we keep executing it. So now let us see what happens if we change the value for this counter and then run the program. So I change it to 5, and when I again run it, accordingly the 5 values are printed. So similarly, we have tried an example for recursion logic or a factorial program. Here we have set the input to be 5. So when you execute, the factorial of 5 gets printed. Let us try altering this value and running it again. So the output is accordingly printed. Let us look at the intermediate code for factorial. So this is our function for a factorial, and as you can see here we have the base condition being if it is m is less than a, that is m is less than 1 being the base condition, we would return the value of m at that stage. So if you go on to the false part, we can see that we decrement the value of the parameter m by 1, push it to our stack which keeps track of parameters for each function call, and then call the factorial function again. So thus it being calling itself again and again, we follow the recursive method here. At the end, once the control returns back during the base case, what we have to do is the value from the stack is popped and it's multiplied with m. So ideally what happens in this situation is m into whatever is the previous execution's result is multiplied here, and the final value gets stored in the stack. So once the control returns back to the first function call here, we pop the value out of the stack and then we print it, so that the value in the top of the stack will be the factorial at that point. So next, let us have a look at a stack example. So the output here is 30 and 20. Let us just take a look at the program. So this is just a simple example where we have pushed 10, 20 and 30. So 30 being the top, that was popped first, and then we popped again and 20 was printed. So that concludes the demo and presentation of our language. Thank you for watching.